So let's go to heat engine and refrigerating machine. So a system operating in a cycle and producing a net quantity of work from a supply of heat is called an heat engine. Now, so a representation of a heat engine. So if you have a temperature T1 here, so this become your hot reservoir. So this is your hot reservoir, or we call it the source of heat natin. Then you have your E, so punta doon. Then you have here your E. Then you will do an heat absorb. Then you produce a work. So you supply a heat absorb. You provide a heat, and it is absorbed by an engine. Then a heat is rejected to the cold reservoir. So this is your T2, and you have your Q rejected going from your engine to T2. So this is now your cold reservoir. So reviewing from your thermodynamics, no, that will be your receiver of heat. Now you absorb the source of heat from T1, then yung engine absorbs the pinadala mo sa engine, and then you produce a work. So you have your work produced papunta dito. Okay? So that is a sample of an simple supply heat, o tinatawag na heat engine. So from there, reviewing from your thermodynamics, so we can do an energy balance. So summing up, that will be your work, that will be your Q absorbed minus your Q rejected. So by means of energy balance. So this is by means of energy balance. And also we can efficiency of the system of the engine, that will be yung work divided by your Q absorbed. So that will be how much yung work mo na pinreduce doon, and also a ratio ng heat na sinupply mo doon sa engine. Or let's say that will be Q absorbed minus your Q rejected divided by your Q absorbed. So we have here schematic diagram, no? So from T1 cold body, you have heat absorbed by the refrigerating machine or compressor. So you will going to supply a work. Now it will be rejected to the environment, T2 to the surrounding. So this is a small this is the representation of a refrigerating machine, where the machine R absorbs the heat. Then you have your Q absorbed from the cold body at the temperature T1. So you have here T1, no, and rejects the heat. Okay, so to QR to the environment. So you need to have a work supply to the system in order for you to achieve yung lower temperature, and also yung init niya, it will be thrown away to the surrounding. So notice nyo dito, class, so mapansin nyo, here we supply the work, and the other one we produce a work. So usually this is the applications ng tinatawag na heat engine. So this is the applications of an we call it internal combustion engine. Yan ang mga application niya. Okay. So yan yung kanyang schematic diagram. Now for this one, This is already in terms of electric motor na ito. Kasi you supply a work. Electric motor. So, you supply a work. So, usually, you can connect that one in this one. So, pwede mo yan. Kasi you supply a work, then connect mo dyan ang refrigerating system in order to function. Okay? So, mapapansin nyo, yung ito heat engine. So, this is reverse naman pag refrigerating machine. Now we can do an energy balance from here. So we can do an energy balance do sa system niya. Energy balance. So what we have here, your work is equal now to your Q rejected minus your Q absorbed. And we have your COP, so your COP, that is the coefficient, no? So coefficient of performance, so that will be your Q absorbed, the ratio of your Q absorbed to the work work supplied to the system. Or we can say that this is now your Q absorbed, then this is now your Q rejected minus your Q absorbed. So you will notice that yung pinagkaiba ng kanina, no? Take note, no, class, no, the performance of an engine, so that is being expressed by in terms of thermal efficiency. So pwede na yung to determine kung gaano ka effective, kung gaano ka ganda, or let's say kung gaano ka we call this the term when you say efficient, no? So that is yung mga heat engine, that is means by thermal efficiency. Now for the performance of a refrigerating machine, so that is expressed by the ratio of useful result to work. So yun naman ang basis ng refrigeration. Kung gaano ka ganda yung system niya is by means of the coefficient of performance. So I'm bringing down here the Carnot cycle, no? So I'm bringing down the Carnot cycle because it has a relationship with the called it a refrigerating system. Now, during the Carnot power cycle, so it is composed of, reviewing from your thermodynamics, no? It's composed of the following reversible process. Now, during the process to A and B, that will be the isothermal expansion, where your TA is equal to your TB and also equal to your T1. Then we have the process B to C, that will be the isentropic expansion, where your isentropic at B and is equal to the isentropic at C. Next, we have the isothermal compression, so that will be your temperature at C is equal to temperature at D and is equal to temperature at point 2. Then we have process D to A, that will be the isentropic compression, so that will be your isentropic at D. Sorry about that. Isentropic at D, it equals to the isentropic at A. And we have your Q absorbed, that will be the temperature at point 1, and multiply it by the change in entropy starting from B to A. B to A. Sorry, this is A. Now for your Q absorbed, so it will be T2, that will be isentropic at C, then isentropic at D minus the isentropic at B. So from here B to C, so that is the change in isentropic. So this is the T, temperature, and S. Now for your work, So that will be the Q absorbed minus your Q rejected, no? And it is equal to the value of your Q absorbed, that will be your T1 isentropic at B minus the isentropic at A. Then it will be minus by your T2, that will be isentropic at point C, and isentropic at point D. Now, so, or we can factor the equation by means of rewriting. We can rewrite our equation as the T sub 1 minus the T sub 2 times the isentropic at point B minus the isentropic at point C. So we can rewrite our equation like this. So we can, sorry, this is isentropic at A. This is isentropic at C to A, C to A, where we can also rewrite your Q rejected. So that will be T2 times the isentropic at point D minus the isentropic at point A. So this is now your point A, and this become your point B. So SB minus SA, then you have SB minus SA, so we can factor that one here. You have your SA, so we can rewrite, this will become now your work. Now for the efficiency, we have, that will be the work divided by the total heat, or Q, no? So we can say that our work is equal to T1 minus your T2 multiplied by isentropic at point B minus isentropic at point A, then divided by the heat. So that will be T1, no? T1 minus isentropic at point B minus the isentropic at point A. So finally, so cancel out yung which is common natin doon. Then, sorry about that. So we can rewrite our equation. So cancel out natin ito, which is yung common. We can rewrite our equation as the efficiency, that will be T1 minus your T2, or divided by the T1. Now, the operation of a refrigeration system is like the reverse Carnot cycle. Now, we have the following pinakaiba. We have here your point A dito sa baba. Then the direction of flow starting from here going to point B. Then here to point C. And then we have going down, that will be your point D, and pabalik sa point A. Then we have now for your TS diagram, so this will be your point C, point B, and this is your A, and this is your D. So we have the following cycle. This is your T2, and this is your T1, going in this kind of loop. Now that the reverse Carnot cycle follows the same process as in the power producing Carnot cycle. Now, but the cycle operates in the counterclockwise or reverse direction. So that's why that is called a reverse Carnot cycle. So we have the following processes. We have process A to B, that will be isentropic compression. So we have your isentropic at point A is equal to now point B. So we have the process B to C, that will be isothermal heat rejection, so constant temperature, where your temperature at point B is equal to your point C and is equal to your T2. Then we have isentropic expansion. So that will be the isentropic at point A is equal to the isentropic at point D. Now we have the process D to A. So D to A, that will be isothermal heat absorption. So where your temperature at point D is equal to your temperature at point A is equal to temperature at T sub 1. And we can write that your Q absorbed, so that will be equal to T sub 1 multiplied by the change in entropy from A to D. So that will be change in entropy at point A minus the entropy at point D. Now for the heat rejected, so that will be T sub 2, temperature at point 2, that will be the change between B and C. So that will be temperature, entropy at point B minus the entropy at point C, where our T2, so this will be your equal to, can be rewritten also since yung B at saka A, entropy at point B and A are equal, so we can write it in an equation that will be the entropy at point A, that will be equal to entropy minus the change entropy between A. So since also your C is equal to point D, okay, so it can be expressed like this. Now we have, now for the work, we can also equate our work, that will be your Q rejected minus your Q absorbed. Then substituting the value of your Q rejected, that will be your T2 entropy at point B and entropy at point C, that will be minus your T1 entropy at point A minus the entropy at point D. Now factor that one, that you will have your T2 minus your T1, and we can substitute substitute the other value. So this will become change this one, it will become entropy at point A and entropy at point E, since it is already in equal. So we can factor that one. You have your entropy at point A minus your entropy at point D. Now for the COP, we have the value, so that will be your Q absorbed divided by your work, or we can substitute the value of your Q absorbed here, or this is A, so that will be your T1 times your entropy at point A minus the entropy at point D, then divided by your work. So the value of your work, that will be your T2 minus your T1, temperature at point 1, times the entropy at point A minus the entropy at point D. So let's cancel out what is common. So your COP will now equal to your T1 divided by the change in temperature T2 to T1. Okay. So now we have the overview of your reverse Carnot cycle and also the Carnot cycle. So let's proceed to a sample problem. So sample problem. So a refrigerating system operates on the reverse Carnot cycle. The higher the temperature of the refrigerant in the system is 120 degrees Fahrenheit and the lower is 10 degrees Fahrenheit. The capacity is 20 tons. So take note, that is not weight, yung tons na yan, that is refrigerating capacity or refrigerating load. So when you say tons, that will be tons of refrigerant, not tons of weight. Okay, so magkaiba yan. take note of that one class. So neglect the losses, so determine A, the coefficient of performance, B, heat rejected from the system in BTU per minute, C, the network in BTU per minute, and D, you have your horsepower. So first things first, so let's, para madali natin maintindihan, let's draw the, call this the TS diagram. So we have your temperature here, and you have your entropy here. So let's draw the TS diagram, like this. Now, so we have the given temperature sa problem, no? So at T1, so take note take note of that one. So every thermodynamic, take note, no? So every thermodynamic problems, so take note of this one, that temperature and pressure must be in a form of an absolute value. So for T1, we have given the lower temperature, so that will be 10 degrees. So this is 10 degrees Fahrenheit. So in order to make it absolute, so we add 460 to convert it into Rankine. So we have 470 degrees Rankine. Now for your temperature at 0.2, so this is now your, we have here your T1, and this is our T2. Now for T2, we have so the higher temperature, we have 120 degrees Fahrenheit. We have here plus 460. We have the value of 580 degrees Fahrenheit. Now we have the given also that the Q observed is 20 tons TR. So that is acronym for tons of refrigerant. So we can draw the cycle starting from here. This is your letter A, then you have your letter B going up here, and this is our letter C, and we have your letter D. So we can draw the cycle here, and we have your 580 degrees Rankine, and this is 470 degrees Rankine. Now for letter A, we have your COP. So remembering that the equation for COP, that will be the temperature at 0.1 divided by the change in temperature between 0.2 T2 to T1. So substitute the value we have for T1, which is 470 degrees Rankine, divided by your T2, that will be 580 degree Rankine, minus your T1, that will be 470 degree Rankine. So using your calculation, calculator, we have the value of COP, that will be 4.273. Now for letter B, the heat rejected from the system in BTU. So we have the for 0.2, we know that our COP is equal to your Q absorbed divided by your divided by the COP, divided by the work. Now okay, so we know, so we need to find the value of your work in order to get your heat rejected. So we can rewrite our equation as the Q absorbed divided by your COP, where our Q absorbed, that will be 20 tons of refrigerant. So we have 20 tons of refrigerant, and we can convert this one into, I forgot to write here the conversion. So first things first, I will write the conversion so that we can you will be fully aware. So let's leave a blank here. Now, for the unit of refrigerating capacity, the standard unit of refrigeration is defined as the ton of refrigeration, or simply the ton, denoted by the symbol TR. Okay, so take note of that one. And 1 ton of refrigeration is the rate of cooling required to freeze 1 ton of water. So when we say 1 ton of water, that is weight of the water, no? 1 ton of water at 32 degrees Fahrenheit into an ice at 32 degrees, into an ice, into an ice at 30 degrees in 1 day. 1 ton, so the rate of cooling of water to freeze. So 32 degrees Fahrenheit into, so usually 32 degrees Fahrenheit, that is also the 0 degrees Celsius into an ice at 32 degrees Fahrenheit in 1 day. So we have the comparison that 1 ton of refrigerant is equal to 20,000 pounds, pound force, which is 144 BTU pound force, divided by 24. So we have 1 ton of refrigerant that will be equal to 12,000 BTU per hour, or let's say this will become a 200 BTU per minute. Now for the metric, we have 1 ton of refrigerant that will be a metric unit that will be equal to 12,000 BTU per hour. So multiply by 252 calorie per BTU. We have your 1 ton of refrigerant is equal to 3,024 kilocalorie per hour, or that is equal to 50.4 kilocalorie per minute. Now for the in SI units, so we have your 1 ton of refrigerant is equivalent to 200 BTU per minute multiplied by 1055, that will be joule per BTU, where your 1 ton of refrigerant is equal to 211 kilojoule per minute, or let's say that will be 3.52 kilowatts. Okay, so we have the following conversion now. So let's go back to the problem. So let's go back to the problem now. So that will be 20 TR, that will be multiplied to 200. So we have the conversion 200 BTU per minute. Okay. Then divided by your COP, which is 4.273. So using your calculator, we have 936. That will be BTU per minute. Now for the call this the Q rejected. So let's rewrite our equation of work. So that will be Q rejected, that will be equal to work plus the Q absorbed. Now we have the values for your work, which is 936 BTU per minute. Now we're going to add what it will be the absorbed, which is already 936, and we have the Q absorbed, which is, so we have your Q absorbed, which is 200 tons of refrigerant times 200 BTU per minute for 1 TR. So this is 1 TR ito. This is 1 TR. So cancel out the tens of refrigerant. Then we have now your Q absorbed is, so this is would be 4,936. We have 4,936. This is the BTU per minute. Now for letter C, AB, that will be C. So what will be the work? So work is already been computed, 936 BTU per minute. Then CD, we have the work. So we have 936 BTU per minute, divided by 42.4, that will be BTU per minute. So this is equivalent to 1 horsepower. So cancel. You have the following value using your calculator. So we have 22.08 horsepower to supply dun sa to drive the compressor or the system or the refrigerating machine. So let's have an overview yung ginawa natin, no? So para makita ninyo. Okay. So overview of the problem. Okay. So it's very easy, that it will not be a complicated one. Okay.